Hey everyone, welcome. Today we're going to take some simple numbers and turn them into, well, a story of motion. We're going to see how a single graph can paint this incredibly powerful picture of an object's whole journey, second by second. So let's dive right in.
So let's start with a big question, right? What can you actually learn from these things? I mean, trying to describe motion with just words or a bunch of numbers in a table can get kind of messy. But a position time graph, it gives you an instant, clear picture. It's a tool that lets you see the story of movement in a single glance. Okay, so how do we even build one of these things? Well, it all starts with the basic numbers. We take some simple data, like where something is and when it was there, and we turn it into a clear visual story.
Everything kicks off with a table, something just like this one. It's pretty straightforward, right? It shows us the position of a runner, in meters, at a few different moments in time, which we're measuring in seconds. This is our starting point, our raw data. Now, to turn that table into a picture, we need a frame. And that frame has two parts. We call them axes. The horizontal one, that flat line along the bottom, that's for time. And the vertical one, the one going up the side, that tracks the runner's position. Super simple rule to remember. Time runs along the bottom, and position goes up the side. Got it? That's the key to everything.
All right, now for the magic. We bring it all together. You see that little table on the left? We take each pair of numbers, like at 1 second, the runner is at 5 meters, and we plot it as a single dot on our graph. Then, once we connect those dots with a line, boom, just like that, our numbers have turned into a picture. We have our position time graph.
But here's the really cool part. The real power of this graph isn't just showing those dots we already had data for. Nope, it's the line connecting them. That nice straight line is packed with a ton of extra information. For instance, our original data table didn't tell us anything about 4.5 seconds. But on the graph, it's easy. We just find 4.5 on that bottom time axis, we trace our finger straight up to the line, and then we look straight across to the position axis. And bingo, we can see the runner was at roughly 22.5 meters.
And guess what? We can work backwards too. Let's say we want to know when our runner hit the 12-meter mark. We just find 12 meters on the side axis, go across to the line, and then drop straight down to the time axis. The graph tells us that happened at about 2.4 seconds. So useful.
You know, there's actually a fancy name for what we've been doing. It's called finding the instantaneous position. All that means is it's the exact position of an object at one single particular moment. Think of it like a snapshot in time, not an average over a long period. And this is really important to keep in mind. A graph is just one tool in the toolbox for describing motion. We could use words or pictures, maybe a motion diagram, or the data table we started with. They're all telling the exact same story of the journey, just, in a different language. All right, you're ready to level up? Things get really interesting when we start tracking more than one thing at the same time. Let's see what happens when we put two runners on the very same graph.
So check this out. We've got runner A and runner B, and each one has their own line showing their motion. Right away, you can just see that they're not moving the same way, can't you? Their lines look different.
So this brings up a classic question in physics. Just by looking at this graph, can we pinpoint the exact time and the exact place where one runner actually passes the other?
Of course we can, and the answer, it's literally staring us right in the face. It's that point where the two lines cross over each other, the intersection. That is the one single moment where both runners are at the exact same spot at the exact same time.
So how do we get the details? We just read the address of that intersection point. We look down to the time axis, and what do we see? 45 seconds. We look across to the position axis, and it's around 190 meters. That's it. That's the spot where they meet. Okay, and here's a little sneak peek for what's coming up. Did you notice how runner B's line is steeper than runner A's? Well, that steepness, we call it the slope, tells us something super important. It tells us about their velocity, basically how fast they're going. We'll dig way more into that later, but it's a huge piece of the puzzle. All right, let's pull all of this together and do a quick recap of what these awesome graphs can really show us. It really boils down to 3 simple steps, right? First, we build the graph from a simple data table. Second, we learn to read between the points on that line to find any position at any time. And finally, we look at those intersections to see how different objects interact, like when they meet or pass each other.
So, what's the big takeaway here? It's that these graphs aren't just pretty pictures. They are incredibly powerful tools for analyzing and solving real-world problems about motion. They take what might seem like a complicated problem and make it super easy to see and understand.
And I'll leave you with one last question to chew on. Looking back at our two runners, remember we said the steeper line belonged to runner B? So just by looking at the steepness of those lines, can you take a guess at which runner is actually faster? Think about it, and you'll be way ahead of the game for our next dive into motion. Thanks for hanging out with me today.